Two black substances quietly built the modern world, and neither one was really invented. Both were simply noticed. One came from wood that had already burned once. The other came from trees that died roughly 300 million years before a single human being existed. Chemically, they're remarkably similar. Concentrated carbon, capable of burning hotter and longer than raw wood ever could. And the story of how humans found that, understood, and eventually became dependent on both of them, stretches across nearly the entire span of human history, ending in cathedrals of industry, in choking city smog, and in mine shafts that still occasionally swallow people whole. So where did it all actually begin? It begins, almost certainly, with an accident nobody could have avoided. Wherever early humans built a controlled fire, charcoal was already forming, whether anyone intended it or not. Evidence for genuinely controlled fire stretches back roughly 1 million years, including research at Wonderwork Cave in South Africa's Northern Cape, where archaeologists identified burnt bone fragments and ash layers consistent with fire, maintained specifically inside the cave, rather than simply occurring naturally. And wherever a wood fire burns, charcoal is essentially unavoidable. The outer layer of a burning log combusts fully, but wood buried deeper inside the fire, starved of direct oxygen by the material surrounding it, doesn't fully burn away. Instead, it undergoes a chemical transformation called pyrolysis. Heat driving off water and volatile compounds while leaving behind a lightweight, brittle, almost purely carbon structure. That leftover material is charcoal, and it had been sitting in the ashes of essentially every human fire for hundreds of thousands of years before anyone thought to do anything deliberate with it. We know people eventually did pay close attention to it because of what they used it to draw. In the mid-1990s, explorers entered a cave in France's Ardèche Valley, now known as Chauvet Cave, and found walls covered in. These caves hold detailed depictions of horses, lions, rhinoceroses, and other Ice Age animals, rendered with a level of technical skill that stunned researchers studying prehistoric art. Radiocarbon dating placed some of these images at roughly 36,000 years old, and many were drawn directly in charcoal, with controlled line work and shading rather than a simple smudge. And later cave art at Lascaux in France and at Apollo 11 Cave in Namibia also incorporated charcoal, natural mineral pigments, evidence that across widely separated regions and long stretches of time, different human populations arrived independently at the same basic discovery, that this leftover fragment of burnt wood could leave a controlled, lasting mark. But charcoal's real transformative power had nothing to do with art. It had to do with heat. Ordinary wood fires typically charcoal can burn in a range of roughly 300 to 400 degrees Celsius. Given adequate airflow, it can burn dramatically, hotter, and with forced air from something like a simple bellows, temperatures can climb past 1,000 or even 1,200 degrees Celsius. At those temperatures, something becomes possible that a plain wood fire could never achieve. Rock begins to melt. Malachite, a green copper-bearing mineral that early humans had already been using as pigment for a very long time, melts at just over 1,000 degrees Celsius. And at that temperature, the carbon in burning charcoal does something chemically remarkable, stripping oxygen atoms directly away from the copper oxide in the ore, a reaction known as reduction, leaving behind pure liquid metal.
Metal pulled directly out of stone, using wood that had already been burned once before. That single reaction,
Carbon-reducing metal oxide under intense heat, effectively underlies the Bronze Age, the Iron Age, and everything metallurgical that followed. The earliest known evidence of copper smelting dates to roughly 5000 BCE, at sites across the Balkans and Anatolia, and that every one of those early operations depended entirely on charcoal, because nothing else available at the time burned hot enough to make the reaction work. Iron smelting demanded even more, typically requiring somewhere between 1200 and 1500 degrees Celsius inside a furnace, a threshold of charcoal, combined with forced air, could reach. And critically, some of that carbon didn't just strip oxygen from the ore, it migrated directly into the iron itself, transforming soft, workable iron into a steel. Distinct, independently developed steelmaking traditions, including Tamahagane steel production in Japan and Wootz steel production in India, both relied on exactly this same fundamental principle, charcoal supplying both the heat and the carbon that gave the resulting metal its strength. For thousands of years, in other words, charcoal wasn't simply a fuel supporting metalworking. In a sense, it was metalworking. Without it, there's no sword, no plow blade, no nail, no functioning Bronze or Iron Age at all. But charcoal came with an enormous hidden cost: wood. Producing a single kilogram of charcoal typically consumes somewhere between 4 and 7 kilograms of raw wood, and a single active smelting operation could strip a meaningful stretch of forest within a year. Multiply that across centuries of continuous ironworking, and the toll on woodland becomes genuinely severe. By the late 1500s, England's forests were visibly disappearing, caught between shipbuilders who needed oak for the navy and ironworkers who needed charcoal for smelting. In 1615, facing this exact shortage, King James I issued a proclamation banning the use of wood and charcoal specifically for glassmaking, forcing that industry to look elsewhere for fuel entirely. And this is roughly the point where coal enters the story, not as some brand new discovery, but as an old, familiar substance finally becoming necessary, out of sheer desperation. Interestingly, the word coal itself carries a clue about which fuel actually came first. In Old English, the word originally referred to a glowing ember, essentially charcoal itself. What we now think of as coal, the black mineral rock dug from the ground, was originally distinguished with separate terms, often sea coal, because along parts of northeastern England it literally washed up on beaches, or pit coal, reflecting where it was actually extracted. Language itself preserves the order of discovery here. Charcoal held the original claim. The mineral rock borrowed it later. Mineral coal itself, though, had been known to various human societies for an extremely long time before it became central to English industry. In New South Wales, Australia, a coal seam near the town of Wingan, known today as Burning Mountain, has reportedly been smoldering underground for roughly 6,000 years, a phenomenon long known to the local Wanneroo people well before recorded European contact. The earliest known written reference to coal in the Western tradition comes from Theophrastus. It was in the late 4th century. They described unique stones that catch fire. These were used by metalworkers in remote parts
of Greece and northwestern Italy for sustained, intense heat. When Rome later expanded into Britain, archaeological
evidence, including coal ash and cinders recovered near Hadrian's Wall, at the bathing complex in Bath, and at other Roman-era British sites, indicates Roman communities were burning coal to heat both barracks and bathwater, effectively tapping into some of the very same coal fields that would later fuel Britain's Industrial Revolution more than 1,000 years afterward. Once Rome withdrew from Britain, though, organized large-scale coal use seems to have largely faded for centuries, evidence that access to a resource that
alone isn't enough. It also requires enough infrastructure and sustained demand to make full use of it.
Elsewhere in the world, coal use developed on entirely separate tracks. In China, archaeological and historical evidence points to coal
being used as early as the Warring States period, and by the time of the Han Dynasty, coal mining had reached genuinely
industrial scale in support of iron production. Marco Polo, traveling through China centuries later, described witnessing black stones dug from mountains that burned much like charcoal. Evidence. From a European visitor's perspective, of an energy economy considerably more advanced than anything he'd seen at home. Separately, in what is now the southwestern United States, the Hopi people were mining and using coal from exposed seams for pottery firing and heating by roughly 1000 CE entirely, independent of developments happening in Europe or Asia. To really understand coal, though, it helps to understand just how strange and how old it actually is. The coal burned today largely formed during the Carboniferous period, roughly 300 to 360 million years ago, a span of time so far removed from human existence that the entirety of our species' history fits comfortably inside a tiny fraction of it. During this period, vast, swampy forests covered much of the planet, filled with towering plant life unlike anything alive today. And when these ancient trees died and fell, something unusual happened, or rather, failed to happen. They largely didn't decompose. Wood contains a tough structural compound called lignin, and the specific class of fungi capable of efficiently breaking lignin down doesn't appear to have been widespread yet during much of this period. Dead trees simply accumulated, layer upon layer, sinking into oxygen-poor swamp water, gradually compressed and heated over unimaginable stretches of time into peat, then lignite, then harder bituminous coal. Some researchers have since suggested the full picture is more complicated than fungi alone, pointing to shifts in the broader depositional environment as another contributing factor. But the core outcome remains the same either way. An extraordinary amount of ancient stored solar energy, locked away underground, waiting. Burning coal, in other words, means releasing sunlight that a tree originally captured hundreds of millions of years before anyone existed to strike a match. Back in medieval England, this ancient stored energy became increasingly central to daily life. By the 13th century, the northeastern English coal trade, centered around Newcastle, was shipping coal south to London by sea, giving rise to that earlier sea coal nickname. And almost immediately, people began complaining about it. Historical accounts describe Queen Eleanor of Provence, leaving Nottingham in the 13th century, specifically because coal smoke had made the air there unbearable. Quite possibly the earliest. This is a recorded instance of someone fleeing a city over air pollution. In the early 14th century, King Edward I issued a proclamation attempting to end it, to restrict the burning of sea coal in London, threatening serious penalties. A ban that was, by most accounts, widely ignored. The underlying economics were simply too strong. Wood and charcoal were becoming increasingly scarce and expensive for a growing urban population, while coal, whatever its downsides, remained comparatively cheap and available. England's dependence on it only deepened from there. Coal did carry one serious limitation that charcoal never had, though: sulfur. When iron is smelted using charcoal, the fuel supplies relatively clean carbon. Raw coal, by contrast, introduces sulfur directly into the process, producing iron that becomes brittle and largely unusable, a defect historically referred to as cold short. For a long stretch of time, this meant coal could reasonably heat a home, but couldn't reliably produce good metal, leaving iron production still fundamentally chained to the forest, and therefore to charcoal. That changed in 1709, when ironmaster Abraham Darby successfully smelted iron using coke, essentially coal that had been heated in an enclosed space. This process was used to drive off sulfur, other volatile compounds, the same basic transformation charcoal represents relative to raw wood. Darby's breakthrough finally allowed iron production to run on coal-derived fuel at scale, and the consequences compounded quickly. Iron-produced coke helped build early steam engines. Those engines, in turn, were used to pump water out of flooding coal mines, allowing deeper,
more productive mining, which supplied even more coal, which produced even more iron. Thomas Newcomen's early
practical steam engine, developed in the early 18th century, was built specifically to solve the problem of water flooding.
Coal mines. Decades later, James Watt's improvements turned that same basic technology into something capable of powering factories and eventually locomotives. In a very real sense, the Industrial Revolution functioned as a tight feedback loop. coal enabling iron, iron enabling engines, and engines enabling still more coal extraction. It's worth pausing on what that actually means. Much of the Industrial Revolution's raw power came not purely from human cleverness, but from a geological accident that occurred hundreds of millions of years earlier. Ancient trees that failed to decompose, compressed slowly into an enormous, concentrated reserve of stored energy, which humans then extracted and burned through in a comparatively tiny sliver of time. That progress came with costs nobody fully anticipated at the outset. In December 1952, a period of unusually still, cold air trapped smoke from countless coal fires, power stations, and vehicles directly over London,
producing a thick, choking smog that lingered for roughly 5 days, severely reducing visibility and disrupting daily life across the city.
A later reassessment placed the resulting death toll in the thousands, a genuinely staggering human cost from simply breathing the city's own air, and the disaster directly led to Britain's first major air pollution legislation a few years later. Coal extraction itself carried its own brutal toll, separate from anything related to burning it. Underground mining exposed workers to methane.
This hazard is gas. Historically called fire damp, it is an invisible and odorless hazard. It is capable of igniting explosively from something as small as a spark off a pickaxe. The invention of the Day-Davy safety lamp in the early 19th century, a flame enclosed safely behind a fine metal mesh, reduced this civic risk considerably, but also, somewhat perversely, encouraged mining in deeper, more dangerous seams that had previously been considered too hazardous to work at all. Catastrophic mining disasters occurred repeatedly across different countries over the following century. Incidents in China, France, and Wales among them, killing hundreds or, in the worst cases, well over 1,000 miners at a time. And before those explosions, there were the children. A British government commission investigating mining conditions in the early 1840s uncovered deeply disturbing
testimony from young children working underground, some spending extremely long shifts alone in near total darkness operating
ventilation doors, others crawling through cramped tunnels hauling loaded coal carts by hand. This testimony genuinely shocked the wider public and helped push through legislation in 1842 banning women and boys under the age of 10 from working underground in British mines, a real reform, though notably one that still left considerably older children legally working in the mines. For years afterward, there are two quieter, connected chapters to charcoal's story worth mentioning as well. Ancient Egyptians, which as far back as roughly 1500 BCE, appear to have used charcoal to help purify drinking water, relying on the same basic principle, adsorption, that underlies modern activated charcoal filters today, contaminants physically binding to charcoal's extraordinarily during the 9th century CE, combined with saltpeter and sulfur in specific proportions to produce a rapid, controlled combustion essentially. A very fast fire, using the exact same carbon-rich humans had first stumbled across, in the ashes of an ordinary campfire. Even coal's waste products eventually reshaped the modern world in unexpected ways. Coal tar, a thick, foul byproduct of coking coal for fuel, was originally treated as largely useless. In the mid-19th century, though, a young chemistry student attempting to synthesize the anti-malarial compound quinine from coal tar derivatives accidentally produced a vivid synthetic purple dye, instead, the first synthetic dye of its kind, helping launch an entire chemical industry. From that same coal tar research eventually came early antiseptics, precursors to modern pharmaceuticals, and a range of other chemical compounds that quietly underpin much of modern chemistry, an entire branch of industry, essentially born from what was originally considered leftover industrial garbage. And coal's strange relationship with fire hasn't fully ended. In the early 1960s, a coal seam beneath the small town of Centralia, Pennsylvania, was accidentally ignited, likely connected to routine trash burning near an old strip mine.
Efforts to extinguish the resulting underground fire failed repeatedly, and it has continued burning for decades since, eventually forcing the relocation of most of the town's residents, as sinkholes and toxic gas seepage made the ground itself unsafe. Some estimates suggest the fire could continue burning for well over a century more. Even that pales in comparison to Australia's Burning Mountain, a coal seam fire that has reportedly been smoldering, essentially uninterrupted, for roughly 6,000 years. So where does all of this actually leave the original question? Charcoal wasn't really invented at all, in the way we normally think about invention. It was simply unavoidable, a natural byproduct, sitting in the ashes of virtually every controlled fire humans ever built, waiting for someone, somewhere, to notice what it could actually do, first as something capable of leaving a lasting mark, later as something capable of unlocking metal from raw stone. Coal, meanwhile, appears to have been independently discovered by numerous different societies, scattered across multiple continents, entirely unaware of one another, a natural consequence of a mineral fuel occurring in exposed outcrops nearly everywhere on Earth. But coal didn't become the dominant global fuel because it was inherently superior to charcoal. It became dominant largely because humanity had already run out of easy access to enough trees, an adaptation born mostly of scarcity rather than any sudden technological triumph. And underneath both stories share the same basic chemistry. Charcoal is concentrated carbon drawn from wood that lived and died relatively recently. Coal is concentrated carbon drawn from trees that lived and died hundreds of millions of years before humans existed at all. Different ages, identical underlying reaction, carbon combining with oxygen to release heat and energy. A reaction that quietly powered a staggering share of human technological progress, along with no small amount of its somewhere in the world right now. Someone is still tending a traditional charcoal kiln, producing, essentially, the same material that helped smelt some of humanity's first pieces of worked metal thousands of years ago. Somewhere else, a coal-fired power plant is releasing energy stored inside the Earth since long before dinosaurs existed. The very first person ever picked up a warm, blackened fragment from the edge of a dying fire had no way of knowing what they were really holding. They simply noticed that it was lighter than the wood it came from, and that when they blew gently across its surface, it glowed brighter than the fire ever had. That was enough. Humans have been burning it, in one form or another, ever since.